Yeah, we started like the series with Johnny's talk on identifiable representation learning, which brings out this really nice perspective that if you have this generator model where you have a latent, you first generate your latent factors and then you map them to the to the observed data regime via this mixing function. Without making any further assumptions, you will not be able to identify latents. Why? Because you could always learn to transform these latents by some function and then apply its inverse during the mixing function stage, right? So, what is the way with which we can restrict the type of indeterminacies that are allowed at the latent stage? So, we have two options. I mean we can make assumptions on the latents themselves. So, what distribution these latents come from, or we can make assumptions on the mixing function, and it's always the interplay between both of these assumptions that help us identify the latents up to like some degree. So one version of like identifiability we saw in Yishin's and Yachi's talk was where we used weak supervision in terms of interventions. So using interventional data, we were able to identify these latents along with the assumption that the mixing function is a polynomial. The nice thing about the polynomial mixing function is that it actually reduces your problem from a nonlinear mixing function to basically linear identifiability. And once you have linear identifiability, you can use interventions to further uh, go beyond and like recover your latents. Then we saw our like in the same spirit, we saw another paper by Gautam, which made the mixing function unconstrained. So now you are not restricted by the fact that okay, you need to have a polynomial function, but then you pay the cost for it by assuming that okay, now my latent actually has to be a linear Gaussian SCM. It cannot be like a general latent distribution. And we are still in the same spirit of in the same spirit we are using interventions as a weak supervision signal. You could we also saw Johan Brimmer's talk where you have the same setup, like you can extend Gautam's result, let's say, to a general SCM, but like under the assumption that okay, we have access to paired interventions or counterfactuals now. So we don't just have two distributions where, you know, like some intervention was applied. We actually have access to the sample before and after intervention. So which is like a more stricter assumption, but then that helps you to identify more general SCMs. But so far in all these works, you have weak supervision, right? What about the purely unsupervised case? We did see a work by Jamal, like which says that okay, like if your latent is Gaussian and you have a sparse mixing function that takes your latents to the observed space, then in this completely unsupervised setup as well, you can identify. And in today's talk, we will still be in the unsupervised setting. So we are making more advances over there. Like, okay, we are not assuming any more weak supervision, no interventions or counterfactuals. But what we have is we have a different type of characterization of our mixing function. This mixing function will be an additive function. So you break your latent space into blocks, and then each block is rendered into the image space or like the observed space, and then you add it together. So Sebastian will now present like why this function helps you identify, and also there are some very cool aspects about additivity that it actually helps you to also do extrapolation, which has not really been shown in identifiability works before. So I'll let Sebastian continue from here.
All right, let me share my screen. Um, uh, okay. Okay. All right. No, not share. It's like okay. Okay, thank you for inviting me. Thanks for organizing these kind of reading group. I think it's very nice for the community. Um, as Divyat already mentioned, we're going to talk about additive decoders for latent variables identification and Cartesian product extrapolation. This is joint work with Divyat, which is first co-author on this work, Yohannes Mitiagas and Simon Lacoste-Julien. Okay, so the first motivation for this work is to sort of understand why object-centric representation learning methods work the way they do. Okay, so algorithms such as slot attention or EADIN use some specific kind of decoders, and basically they uh, are able to perform some kind of disentanglement by only minimizing some kind of reconstruction loss. Okay, so for instance, you have an example from the slot attention paper below here. And you can see that this architecture with this very simple task of reconstruction is able to sort of segment the objects and represent them in different slots. And so the interesting thing here is that this is completely unsupervised, right? So there's no label, there's no segmentation labels here when we train. And so I think there's like a an open question here of like why is this even happening, right? And do we have like a good explanation for why this kind of segmentation occurs? And so in this work we try to do a small step into starting to explain why this is working, maybe in a more theoretical manner. The second motivation has to do with compositional generalization. So in the paper, we call it Cartesian-product extrapolation, but you can think of it as really compositional generalization. So yeah, we know that humans can imagine things they have never seen before. And one way they do that is by recombining known concepts in novel ways. So if I show you, these three combinations of features, you can certainly imagine this fourth combination, even though you've never seen a blue apple before. Okay, so in a sense, you're sort of combining the feature of being blue with the feature of being an apple. Um, and we know that modern generative AIs are able to do that to some extent, right? So everyone has seen this nice example from DALI. Um, and there is like a question of whether like was this chair or like some version of this chair present in the data set before, but it seems like maybe it was not part of the internet before. So maybe like somehow this method was able to really recombine like the notion of chair and avocado together. And I think there's really like an open question here of like how is it even able to do something like that. And so yeah, again in this work we do like a small step toward trying to understand that. And so, yeah, to start tackling these questions, we introduce, a simple architecture we call additive decoders, which is similar to object-centric decoders people use in practice, but for which we can prove both disentanglement and extrapolation guarantees. So that's really like the summary of the contribution. So let me explain what I mean here by an additive decoder. So X here is an observation, like an image. F is your decoder. Z is the vector of latent factors. Calligraphic B is going to be a partition of the dimensions of Z. Okay, so it's a set of blocks basically. So here in this example, we have like two blocks of 2 dimensions each. And each function here, each block specific function here takes as input a sub-block of, and so ZB is basically like the corresponding sub-block of the vector Z. And of course, because it's a partition, these blocks are non-overlapping. So that's what we mean by being additive. Now, here's an example where this function class makes sense, right? So here we have that the observation is an image of balls moving in space, and it turns out that you can represent this image as a sum of two ball-specific image. And here, really, the sum happens in pixel space, right? So that's really where we take the sum. And we have that each block-specific decoder FB takes as input like the position of the ball, so that would be the latent block ZB, and outputs the block specific image, which here is the image of a single ball, right? Okay, so we have at least like one example where this additivity assumption makes sense. So let's run with that. Yeah, so as I said, the blocks are the positions of the ball here. Okay, so now I want to go into the details maybe of how is this really related to object-centric decoders. So here you have like the comparison basically. So below you have maybe the standard object-centric decoder. So it turns out that these decoders are not additive, right? Because this so let me try to find my pointer. There you go. Okay, so these decoders are not additive because of this masking here, right? So, just visually they kind of look the same, right? Because you have a sum here over latent blocks. So that's already, point of similarity. But the only thing that makes them not really additive is this masking mechanism here. So basically this mask is what it's doing is it's deciding for each object which pixel are part of this object in a sense. That's one way to see it. And the way it's computed is via basically an extra channel that you add in your decoder, that is sort of deciding, that's giving a score for like, okay, every so AK of ZB would be the score of pixel K for object ZB, and then you normalize across objects, across blocks, and that gives you your mask. And yeah, so the point here is just that because of this normalization here, the mask depends on um, on all the latents, and thus this function is not additive. But they kind of look the same, so maybe it's a good first step to start with additive decoders. Okay, so and an example of something that can be expressed by an object-centric decoder, which cannot be expressed by an additive decoder, is a simple image where occlusion occurs. Okay, so that would be an example here. And you can sort of convince yourself that this is the case. I'm not going to do that. I have like we have a paragraph in the paper that sort of try to argue for this, but you can see it quite easily with some thinking. Okay. Okay. So this is basically the setup, right? So we want to just train this model to perform reconstruction and see if this is enough to get disentanglement. So just introducing some notation, g hat of x is going to be our encoder, and f hat is going to be our decoder, which will be additive, of course. Now the question is this: if I solve my reconstruction problem, i.e. if I minimize this loss, can I guarantee disentanglement of the latent blocks? And so intuitively, what we mean by disentanglement is the following here. So if I take an image, I pass it into my encoder, I get my latent blocks ZB1 and ZB2. Then I can pass these latent blocks into their respective block-specific decoders. That would be FB1 and FB2. And these give me the block-specific images. And we would consider this case disentangled because we have a nice segmentation of the objects. Whereas here we would say the decoder is entangled because you don't have this nice one-to-one correspondence between the objects in the scene and the block-specific decoders. So this is like the high-level idea of disentanglement. And so as you know, the main theoretical result of this work is to show that disentanglement is actually bound to happen when solving the reconstruction problem, under some assumptions, of course. Okay, so everyone here, I think, is pretty familiar with the idea of like a data generating process. So, but I have to have a slide here. So the idea here is that to start making theory about disentanglement is, we need to talk about like, a notion of good representation, or like the real representation. And that's what we mean by a ground truth decoder. So we will assume that it's also additive, of course. And basically, this decoder is sort of capturing the relationship between the images and the natural factors of variation that we somehow have in our mind. Okay. And we already saw an example of a ground truth decoder that makes sense. That would be like maybe a good example of a ground truth decoder, right? So here the observation is image, and the natural factors of variation would be the latent factors and the positions of each ball precisely. Yeah. Okay. By the way, like feel free to interrupt me if something is not clear. Just like I cannot see the chat really, so just let me know, shout something. Okay. So okay, now we have this idea of ground truth decoder, so we can define what we mean by disentanglements mathematically. So we're going to say that a learned decoder f hat is disentangled with respect to a ground truth decoder f if the learned block-specific decoders imitate the ground truth ones. Okay, so mathematically we mean the following. So we have that basically the learned block-specific decoders are equal to the ground truth block-specific decoder up to a permutation of the blocks, up to an invertible transformation of the latent blocks, the latent vectors, ZB, and up to an additive constant. And it turns out that this additive constant, when you take the sum of all the decoders together, will just disappear in a sense. It will equal 0. And so, yeah, so maybe just to explain it a bit more, this permutation here, pi, is we say that it's a block, it's a block preserving permutation, right? So it means it will map the blocks to other blocks, right? So you're not allowed to sort of mix blocks together. You can just move one block to another block. You can mix things within a block, but you cannot like break blocks. That's one way to see it, maybe. So that's for the permutation. And here we have this invertible transformation. And so the way I think about it is that we really don't care about the basis in which the position of the objects is chosen. Okay, so basically we are going to be able to separate the objects from each other, but the exact basis in which we express the position of the objects won't be recovered uniquely, right? So I think that that kind of makes sense intuitively. Like, who cares which basis you're using to represent the position of an object? So I think that kind of makes sense. Okay, so this is like one definition that I think is maybe, tailored to this idea of having like block specific decoders. Um, Here I'm sort of relating it to the usual definition. So the usual definition, right, is here basically, right? We say that, you know, uh, a learned decoder is equivalent to a ground truth decoder if both are related via a basically a this very specific map, which is a permutation of the blocks composed with a blockwise diffeomorphism, right? So you transform each block individually and then you permute the blocks. And to show that these two are equivalent, you just have to start from the definition. You have this for every block. For every block, you can take the sum over blocks, and you get the usual definition. It's just to sort of connect with maybe the usual definition. Uh, so far, so good. Any question at this stage? Okay, I'll just continue. Oh yeah, and so yeah, from this equation we have that v is going to be the transition function from one netted space to another, right? So, um, just by applying f minus one on both sides of this equation, you get that equation. And so really the way I think about v is really, it starts from the latent, like the learned latent space. It maps to images, and then you take the images and you look like what's the corresponding ground truth representation. So you have like a function that translates between learned and ground truth representations. That's really like it's going to be like the important map here. Um, okay, so now, so since I know this audience is kind of used to like identifiability theory, I decided to go into like more details of the results, and also we have time, so that's great. So let's do that. So now we're gonna go into the details of the identifiability guarantees. Um, so okay, we are going to assume that there is a data generating process. So X is basically just this mixing model, right? Or this deep generative model where the latent is sampled from some distribution PZ train, and the decoder is additive. We're going to call the calligraphic Z train. So yeah, so Z train here is the support of this distribution. Z hat train here is the support of the learned latent, right? So this corresponds to basically like pushing your data set into your encoder and looking at the possible learned latents that you can reach, right? So that's the support of the learned latents. And so as I said before, like if the manifolds of two of the ground, if the ground truth manifold is equal to the learned manifold, you can define this function, which is just transitioning from one space to another. Okay. Um, and yeah, so of course this will occur just by solving the reconstruction problem, which I think is maybe intuitive here. So okay, so that's the setup, that's the notation. Okay, so now we can go into the technicality maybe of the result. So at a high level, the proof is separated in two steps. So first of all, we show local B disentanglement. So B here stands for block disentanglement. So it's just as I explained before. Um, as opposed to global disentanglement, right? So we're going to have like a first result which gives you local disentanglement, and then by adding more assumption, we're going to get global disentanglement. And maybe before going further into the assumption, I can sort of explain the difference between local and global. So basically, when I say local disentanglement, what I mean is that um, the Jacobian always have a block structure or a block permutation structure. So for every z, the Jacobian has a block preserving so a block permutation structure. And maybe the problem here is that this with this definition, if you change z, if you look at the Jacobian at different places in the space, the permutation can change, right? And if the permutation changes, then you won't have like what we want in terms of like actual disentanglement. So global disentanglement is really like the what we want, which is the statement is that the map V is really basically a block preserving permutation of the entries composed with a blockwise transformation. And so going from this to this is not entirely trivial, and so that's why we need more assumptions. Okay, so that's sort of high level, local, global. I will give some intuition about the difference between these two later on. Um, but okay, so
So
there we go. So yeah, yeah.
Zohab had a question in the chat, which I think your theorem statements answer. Is that
So I cannot
answer
see
the
the.
question? It said so far it sounds like we're going to find out that our additive decoder discovers the same partitions as the ground truth. Is that a correct understanding? And I guess that's theorem two. I mean, these are two different senses.
So the partition. So by learning the partition, do you mean like the partition of the latent? So here we assume that the partition is known actually. So the partition of the so B we assume is the calligraphic B is the same in both the ground truth model and the learn model. So we don't learn it. I suspect it could be learned, but that's like future work. Um,
Okay.
so it's not really so like local versus global is kind of
A
a
different,
different thing. But I will
yeah.
give more details on that later to give some intuition of what can go wrong, basically.
Okay. And when you say that you know the partition ahead of time, that just that it's divided into spaces with this many dimensions, like that's all I
Yes,
can really imagine you specifying.
yes, yes,
Okay.
yes. Yeah. So you know the dimensionality of the latent vector and you know how it's partitioned.
Yeah, like for your balls example, it would be say 3 and 3 or something. I mean, RGB maybe is three-dimensional, so maybe 5 and 5, like X and Y position plus
Yeah, so that would
color.
be so if you go back, um yeah, so here you would just so what you would know is basically this. Okay, so that's all the
Yeah.
information you need. So it tells you how many latents you have and how they are segmented.
Okay. Cool. And color you're just using to kind of distinguish the balls. It's not like something you assume is actually part of the latent
So it's not,
representation. It's
yes,
just,
that's
yeah.
a good point. That's a good point. It's not part of the latent. It's sort of encoded into the identity of the block specific decoder, right? It's like
Right.
so
Yeah.
but that's a good question. Like there are like some issues that can arise with like with coloring. But so for instance,
Cool.
color is like a category, and here we really need the latents to be continuous. So I
Right.
mean, I guess you could also see it as I don't know, for me, color is like more categorical, but yeah,
Mhm.
anyway, so I haven't thought about it that much actually,
Cool.
but
I think this answers the question from the chat is, yeah, you know the size of the blocks. And given that information is input, your results say in two different senses that we discover the correct partition of the latent variables. So I'll let you go on. Thanks.
good, good. Okay. Okay, so let me just walk you through the assumptions quickly. Okay, so this is the first step here is both the ground truth and the learn decoders are additive and C2 diffeomorphisms on their image. Okay, first assumption, that's kind of standard. Well, additivity is not standard, but C2 diffeomorphism is standard. So data generating process, that's something I already mentioned. We assume that the decoder is continuous. Okay, that's pretty mild. Importantly, we need the ground truth decoder to be sufficiently nonlinear, and I will explain that later on. And I need also like some kind of topological condition on the support of the latent, which is regular closed. Okay, and I will explain also what this means. Basically, this is what I mean by continuous. Like I need to be able to take derivative everywhere. That's kind of the idea. Um, so with this assumption, I get local disentanglement. If I add more assumptions, so if I add that my support is path connected, which basically means that the support holds in one piece. And if I assume that both the learned and ground truth block specific decoders are injective, then I have that I have global disentanglement. Okay, so this is sort of the all the results, identifiability result in one go, and I will try to explain these assumptions now.
And will you give a counter example that we can't get global disentanglement only from the first set of assumptions?
I'm
Or
not
it's
sure
like it's so clear that you don't
close.
need to like explicitly construct the counter
No,
example.
it's no. So I will. So I give examples of function v that is locally disentangled in a sense, which is so I think it's kind of answering your question, but
Yeah,
I'll get
I
there.
think so.
I'll get there.
Cool.
Yeah. Yeah. Okay, so this is the topological condition. So basically I have here regularly closed versus not regularly closed, and I have path connected versus not path connected, and you have like different combinations of these assumptions. For global disentanglement, I need both conditions, and for local disentanglement, I need only regularly closed. Path connected is not necessary, and so maybe so path connected I think is really intuitive, right? It just means that you can link any 2 points in the set by a continuous path that stays in the set, right? So clearly this is path connected. This is also path connected. This is not, right, because I can, like, if I take a point here and I take a point here, I cannot connect them. Okay, that's intuitive. For regularly closed, so the technical condition is that the closure of the interior is equal to the set. That's what it means to be regular closed. So you can see here that if you take the interior of this set, you will sort of lose this sort of thin piece, right? And then when you take the closure again, this piece will have disappeared basically. So you don't have that the original set is equal to the closure of its interior, right? So it's not regularly closed. And this is because if you have two functions that are equal on a set like this, it's possible that their derivative here won't be equal. And in the proof, I need to have equal derivative everywhere. So that's kind of why I need this assumption. But anyway, technical detail maybe. Okay, so that's for the topological conditions. And now I want to give examples of local but not global disentanglement. So here I just specify the function v, right? So the transition function from latent to from learned latent to ground truth latent. And the function is pretty simple. Basically, so basically here I have a disconnected support, right? So the support of the latent is the union of these two squares. And on this region, the function v is just the identity, right? And when I'm in this region, the function is like just a permuted identity, if you want, right? So that's what I'm saying here. And so, of course, if you take the Jacobian of this function, you're going to have that, everywhere the Jacobian is a permutation. It's a permutation times a diagonal matrix, right? So it has a permutation structure. But the function is not globally disentangled because I cannot write this function as, so for instance, you can see that the v, so if I look at v1, v1 depends both on z1 and z2. That's kind of the idea. So it's not globally disentangled. Okay, that's the first example. Second example is you can have problems even if the support is connected. Yes, that's why you need more than just path connectedness. And here I have this weirdly shaped support, and that's how I specify the function. Okay, so the first component of v1 is just z1 directly, and v2 is this weird function. Okay, basically it has some value, some. Actually, you don't need to parse that. Okay, I have like made a very beautiful drawing here to give like an intuition of what can go wrong. So the idea here is that, okay, so maybe first of all, before going there, you can already see that if you take the derivative of this function with respect to if you look at the Jacobian of this function, you will always have that it has a diagonal structure, right? So it's locally disentangled. But because of how things are set up, you have that this the dimension v2 depends both on z2 and on z1. So you don't have global disentanglement. And so what I'm trying to express here is you have one branch here which is sort of higher than the other, and so the value changes when you vary z1. Okay, so that's the idea. Even though the gradient is always zero, the partial derivative with respect to z1 is always zero, you don't have a function which is constant in z1. Okay, that's the idea. But this is, yeah, okay. So if you have more question on this, I can try to answer, but I'll just move.
Which of the assumptions is example 7 violating?
Yeah, that's a good question. So here it's a little bit difficult to know, because here the way I'm so here I just start with the transition function directly. So it's hard to know is this transition function realizable with additive decoders? I'm not even sure if that's a possibility,
Okay.
right?
Because this
So
is
it could
path
be that it's just
connected
there's,
and regularly closed.
yeah. So I think it's either additivity or
Okay.
injectivity of the block specific decoders.
Not one of the
This one.
topological / the conditions from that slide. Yeah. It's one of the
So
other
this
thing.
one, yeah,
Yeah. Okay.
injectivity. So because the support is clearly path connected, but it could be maybe that these functions are not injected. It could even be that this v cannot be realized as with additive decoders. That's also a possibility. I'm not sure.
Gotcha.
So yeah. All right. Okay. Okay. So here so I spent a lot of time going into the details of these assumptions, but something cool about this result that I want to emphasize is that we make very, very weak assumption about the distribution of the latents, right? So you can have dependencies, you can have very weirdly shaped support, right? We just need the path connectedness. And so it means you could have causal dependencies between your latents, all sorts of stuff. The what does the work for you here is really the additivity of the decoder. Okay, so we don't really use the structure in the latent space here. Okay, so that's one point. Okay, so I said I wanted to talk about this sufficient nonlinearity condition. What do I want to say about this? Okay, so first of all, I can already say that the proof is based on the proofs from Apo-Ivarinen's group. Okay, so this 2019 paper, that's we basically took this proof and sort of apply it to the additive decoders and sort of just worked out of the box. So in terms of technical contribution, we have this discussion on path connectedness and also this notion of having blocks, but the proof structure is very, very similar. So I have the details in the paper. I won't have time to go here, but so the point is that this assumption is reminiscent of the sufficient variability from Apple's group. It's just here you now have this notion of block. You have, if you remember, also in these results, you also have something about the second derivative of the log conditional density, right? That appears. That's kind of what you see here. And so so you have this sort of weird matrix that you require to be full rank. Okay, I don't have a super strong intuition of exactly what it means. But yeah, so that's if you want to sort of help me understand this, I would be happy. But I'll just go quick. And also I have assumptions. So the way I try to think about this assumption is just coming up with example and see when it's satisfied and when it's not. So okay, hopefully the words, the terminology sufficient nonlinearity makes sense because linear functions don't satisfy this condition. Okay, so that's already good news. So really here something that I think is interesting is that nonlinearity is actually helping you, right? It's really key for this result to work. And here I give a simple function that satisfies this condition, this sufficient nonlinearity condition. So it's not an assumption that makes the result completely vacuous, right? Some function will satisfy this condition. And yeah, so here also I have an example from that is maybe a little bit more realistic. So here what we do is we implemented a decoder in JAX that goes from a two-dimensional latent to images of balls, okay? And because it's in JAX, it's easy to compute derivative and second derivative. So that's what we did. And we basically just verified numerically that this assumption, seems to be satisfied. And so, yeah, I won't go into the details of precisely how we do that, but that's kind of the idea. So, okay, maybe I can give like the details a little bit. So what we do is we first of all compute this matrix so on a grid in latent space, right? So we have we compute this matrix sort of on the space of possible z's, and then we verify if this matrix is full rank everywhere. That's kind of the idea. And yeah, so the way we do that is by computing this quantity here, which is sort of the four-dimensional volume of the parallelepiped spanned by the columns of W. Okay, so it's kind of a mouthful, but that's the idea. And so the point is that if the vectors are linearly dependent, the volume of this parallelepiped will be zero, and thus this will show up here. And yeah, if it's orthogonal, you'll get one. Yeah.
We have another question from the chat. I'll read it, but this is maybe because you mentioned this being more of an open thing to interpretation. Maybe you'll want to save it toward the end, but it's about that full column rank assumption, saying, does it have something to do with orthogonality of the functions and Schmidt decomposition?
So I don't think it has something to do with orthogonality, because well, it depends on orthogonality of what, but like so 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 there is this work, independent mechanism analysis, right, which basically leverages the orthogonality of the Jacobian. So you want the columns of your Jacobian to be orthogonal. This is a different function class, right? You can have an additive there are additive decoders which don't have this orthogonality property. And so this is a different thing. So this is not requiring orthogonality, right? In the sense it's weaker. We just need linear independence of these differential. Like you also need to go at the second order term. Does that make some sense? So maybe I can give some intuition that I have. I also believe like this condition is geometric in the sense that it's a condition about the manifold spanned by the block specific decoders. And so, and why I'm saying it's geometric, it's because it's actually so I don't have a proof of this, but just like intuition, I'm quite sure that it's invariant to reparametrization. If you reparameterize the decoder, you're sort of like if this condition is satisfied, it will remain satisfied by changing the parameterization. So it means it's really a property of like the set of points of the manifold themselves. And so yeah, that would be nice to have like something a bit something a bit more intuitive there. But yeah, that's where I am right now. Okay. Okay, so now I can talk about extrapolation. How am I doing on time? Okay, I have 15 minutes. That should be...
Yeah, and if possible, having at least 5 minutes for discussion.
Yeah, I can do that. Yeah. Okay, so extrapolation. Okay, so just recalling the notation. So z hat train is the support of the learned factors that we see during training. We define this Cartesian product extension, which I think is like easier to understand with a simple picture. So if your set of latent is this L-shaped set in R2, its Cartesian product extension is going to be the smallest square that contains it. Okay, and so it's it's usually like not usually, it will always be like a superset of the original set. And the way this definition works is that basically we project this set on the axis, and then we take the Cartesian product of this projection. That gives you the Cartesian product extension of the set. Okay, so that's for Cartesian product extension. And the main result that we have in terms of extrapolation is this. So basically what we say is that under the same assumptions as the previous theorem, so the global one, we have that the learn decoder imitates the ground truth decoder, not only over the set of observed latents at training time, but over all of its Cartesian product extension. Okay, so what this means is that you can sort of generate samples that you've never seen during training, but that are still on the, the ground truth data manifold. Okay, so that's how I like to think about it. And so more precisely, that would be the explanation. So what we do is so v bar here is basically an extension of the function v, right? So the function v was from z hat train to z train. Now v bar is sort of the natural extension to the Cartesian product extension. And yeah, so now we have this, the statement that I mentioned before is this, right? So we have that, for all the latents in the Cartesian product extension, I have that, my learned decoder gives the same output as my ground truth decoder when I compose with v bar. Okay, so another way to see it is with this map. So basically we have that this mapping commutes, right? So what it means is that going from this set to this set is the same as going from this set to this set. Okay. And so yeah, so okay, maybe at this point it's a little bit abstract. I think it's maybe easier to understand with examples, right? So with experiments. So actual, like, what can we do with this? Okay, so here are the data set that we consider. It's very, like, experimentally, it's it's fairly simple, at least conceptually simple. It was kind of hard to train, actually. You can talk with Deviat about this. But yeah, so we consider very simple data sets. So the first one is the scalar latent data set. We just have balls moving up and down. Okay, so the dimensionality of the latent is 2, and the blocks are basically scalar, right? So it's just going up and down. We have another data set where balls are able to move in different directions. And so we have this non-trivial blocks structure here appearing. And we also have like two different cases, independent and dependent, okay, because we wanted to highlight the fact that our theory works even in the dependent case. Okay, so we have some numbers here. So what we do is we train an additive decoder and a non-additive decoder on these data sets, and we measure some kind of MCC score. It's not exactly the MCC because we're looking at blocks, right? And we also want to be invariant to nonlinear transformation, right? So we don't want to test for linearity, right? We just want we want to know if there is a nonlinear transformation between the two blocks. So I think for scalar blocks we use the Spearman correlation, right? So MCC with the Spearman correlation, which is just like a rank test. And for the blocks we use some kind of tree, but I don't remember the details. I would have to ask to Didiat. But anyway, so this is basically a variant of MCC where we do some kind of pairing between the learned blocks and the ground truth blocks, okay, to compute these scores. And so yeah, so we see that the additive decoder is like much more disentangled. And also we can verify this maybe visually. So here we have original images, we have the reconstruction. So okay, reconstruction is almost perfect. And we can also render each block specific decoder individually. So that's what we get. We can see that each block specific decoder is corresponding to a single ball. Okay, we can see that visually, and that's great. Also, maybe you can see that there is like some kind of visual artifact here, right? Like the images are a bit weird. This is due to the constant indeterminacy, right? The additive indeterminacy. And the cool thing is that when you take the sum, right? So if you take the sum of these two images, somehow you get the right image, or you get the right color, like the artifact disappears. So I think it's kind of cool to see this like the theory appearing somehow in the experiment. Okay, so that's for disentanglement. Okay, now for extrapolation. How do we verify extrapolation? What we do is we take this data set. So this is the scalar data set. The balls can only move up and down, very simple. And what we do is we just remove a portion of the data set, right? We just say, okay, every image where the balls, like where both balls are in the upper half of the image, we just drop these images. We just don't train on them. And so we get this this L-shaped support in latent space. and then we train and see what happens, right? So we train with both an additive decoder and a non-additive decoder. And also I want to emphasize that we're not showing these numbers here, but like when we train additive and non-additive, we verify that the reconstruction laws are similar, right? So they have like very similar reconstruction abilities. It's just really the representation that is different, which is in line with the theory. Okay, and of course, what we see here is the latent space, right? That we learned. So these points, like these colored points in blue to yellow shades, these are basically the output of your encoder, right? So you push your data set into your encoder, and then you render these latent representations in 2D, and that's what we see. So we see that for the additive decoder, everything is very nicely aligned. It's very straight, very disentangled. That's great. For the additive decoder, you get something completely distorted. Okay, so no disentanglement whatsoever. We can then generate the images, right? So we take points in the space and we map them to image space. And we can do a grid and just like render all these images, and we get this. And you can see also visually, right, that this is disentangled here. If you move along one dimension here, only one ball moves, and similarly for the other dimension, right? So you have a very nice disentanglement here, and it's not the case for the non-additive decoder, which is okay, great. And maybe more importantly, for extrapolation, we have that these, even though these images were not part of the data set, we're still able to generate them. Okay, so that's the extrapolation part, and this is because of the very restrictive structure of additivity, right? That's really why we can do something like that. And of course, this doesn't really work with the non-additive decoder, right? If you go outside the domain here, you get weird looking images. So yeah, so that's the idea for extrapolation. I think I'm pretty much done, so we'll have some time to discuss. So yeah, so the way I think about this work is this is really a first step in understanding maybe like extrapolation or creativity somehow in generative models. And I think that identifiability is like one tool that should be used to like understand this phenomenon theoretically. And I think this is kind of like a prototype of how this could be done for more interesting architectures. And yeah, so as I said, the expressivity of additive decoder is very limited. So, this is just a first step, of course. And yeah, we're sort of excited to see like if we can, have this kind of analysis extrapolated to like more interesting models like DALI and whatnot. So yeah, thank you for your attention.